Good morning to all the participants. Welcome you all to the lecture series, Strength of Materials. I am handling the subject, the Strength of Materials for our diploma students. Now, till now we are discussing about the more bending moment and bending moment and shear force. Now, we have already discussed number of issues related to bending moment and shear force for last 4 classes, and this is the 5th class. More probably we are completing today. Now, till now, whatever the things we have discussed, I will go through this in few slides, and then I will solve few problems, and we will discuss about. You can ask me questions at the end of the session. Now let us go ahead with the topic, that is shear force and bending moment. How to plot the bending moment and shear force diagrams. Now already we have discussed about the types of beams. Now cantilever beam, one end free, one end is free, and the other end is fixed. And you know, the another kind of beam is simply supported beam. A simply supported beam has a span like L meter in support. Then a fixed beam. Fixed beam means both the ends are rigidly fixed. For example, now this is the fixed beam. Now this is the fixed beam. The both ends are rigidly fixed. And this is one proper cantilever, where this is the proper cantilever. Proper cantilever means this is the cantilever beam, and this is the fixed end, and there is a simple support. And you know, these are the types of beams. This is overhanging to the left hand side, overhanging portion. This is L1, and this is the L. This is also L1. This is overhanging to the right hand side, and this is double overhanging beam. This is overhanging to the right and overhanging to the left side, and this is a continuous beam. And this is another beam. It is fixed end. The other one is this is the hinge. This is the hinge and roller support. This type of supports are roller support. And you know, types of loads: point load or concentrated load, and UDL, uniformly distributed load. The load is acting for the span or the beam, that is W kilonewton per meter. And this is uniformly varying load. At one end it is zero load. The other end W kilonewton per meter. It is now this is the uniformly varying load, UDL. It is called uniformly varying load, and this is the moving load. And we know in the design of engineering, civil engineering structures, like buildings, bridges, dams, etc. Now they are designed and it should satisfy the conditions. Now these 3 conditions, these are equilibrium conditions. That is the structure will be designed for the conditions. These are the conditions. Now we are more familiar with vertical, horizontal, and horizontal forces. That is vertical axis, horizontal axis. That is x axis and y axis. Therefore, now conditions, there are 3 conditions of equilibrium: sigma v is equal to 0, and sigma h is equal to 0, and moments of all the forces in the loaded beam is equal to 0. Now that means that is vertical force. That is one force is acting upward, the other force is acting downward. That is, sum of these 2 forces must be equal to 0. And similarly, sigma h is equal to 0. Horizontal force, horizontal force, horizontal force, horizontal force. Now all the horizontal forces must be equal to 0. Now similarly, the load is acting on the beam. There is a possibility there is a rotation in this direction. That is rotation. It is clockwise. That is bending. Now that is moment. Moment is nothing but rotation or bending. Now this sigma m is equal to 0. These are the conditions of equilibrium. And we know we have discussed a few problems for solving the reactions. How to calculate the reactions in a cantilever beam. In a cantilever beam, this is the free end. That is the fixed end, fixed support. Now there are 3 point loads acting on the beam. When the 3 loads are acting on the beam, now what is the reaction? Now there is one force is acting downward. There are three forces acting downward, and there is only one reaction. Now it has to resist. All the three forces must be resisted by only one vertical force. Now because all the three forces are acting downward, that is vertically downward, therefore for equilibrium condition, the reaction must be upward, and the sum of this entire, that is forces, that is sum of, that is algebraic sum of all the forces in this beam must be equal to 0. For that condition, that is sum of the downward forces, three forces, and one sum of upward forces is equal to 0. That is how we can now, as soon as we see the diagram, we can calculate the reaction. The reaction is resisting the support. There is a support resisting the vertical forces. They are acting downward. That is how we can calculate. That is plainly we can say, because it is only one support, all the three forces are resisted by that support. Therefore, sigma V is equal to 0. Therefore, sum of downward forces must be equal to sum of upward forces. And similarly, let us have the one more problem. Now here, to calculate the reactions. To calculate the reactions, that is, there are two vertical forces acting downward. There are two vertical forces, and there are two reactions which are acting upward. So therefore, sum of the downward force must be equal to sum of the upward forces. Now the conditions of equilibrium, that is, we have only vertical forces in this beam. In this beam system, there is two downward forces and two upward forces. Therefore, sum of these two downward forces must be equal to sum of these two upward forces. That is reaction. That is reaction 1 and reaction 2. That is reaction at A and reaction at B. That is simple supports. Therefore, sigma V is equal to 0. When sigma V is equal to 0, it means RA plus RD, that is reaction at D and reaction at A, they are acting upward, must be equal to the forces which are acting downward. And to calculate the reaction, now what is the load taken by this support and the load taken by this support? Now to calculate this, now let us call the one more equation, that is conditions of equilibrium. There are three conditions of equilibrium. One condition is already used. The other condition is sigma H is equal to 0. Sigma H, horizontal forces. So algebraic sum of all the horizontal forces must be equal to 0 in this system. There are no horizontal forces, therefore there are no horizontal forces, therefore that condition is irrelevant. We are not using that. Now therefore the third condition, sigma MA is equal to 0. Sigma MA is equal to 0. Now therefore, taking moment about A, now when you taking the moment about A, that is sigma MA, algebraic sum of all the forces in the beam, in this beam about A is equal to 0. Therefore, now see, now this reaction creates anti-clockwise moment, and this creates clockwise moment, and this creates clockwise moment. Therefore, sum of the anti-clockwise moment is equal to sum of the clockwise moments. Therefore, when you consider the moment of algebraic sum of the moments of all the forces in this beam about A, therefore RD into distance is equal to, that is 40 kilonewton multiplied by this distance, it is 3 meters. It is 3 meters plus 40 kilonewton multiplied by this one, that is 1 meter from here to here. Now that is what we have written here. Therefore, sigma. From this we can calculate RD is equal to, that is 40 kilonewton. And we know already we have written here sum of the upward forces must be equal to sum of the downward forces. It will be the RD plus RD, total load 80 kilonewton is resisted by these two. From this we have calculated the RD is equal to 40 kilonewton. RD is equal to 40 kilonewton. Therefore, now this 40 kilonewton, substitute this here, now we will get RA is equal to, that is 40 kilonewton. Now, not necessary to do all these exercises. Now, it is strictly speaking, now if you are eligible, you can understand. Now, this beam is symmetrically loaded. Therefore, now at equidistant, the load is at the equidistant from the supports. Now, from here it is 1 meter, from here it is 1 meter. Therefore, the beam is symmetrically loaded. Now, there, when the beam is symmetrically loaded, then straight away we can write down RA is equal to half of the load. Total load is resisted by this, and half of the load is resisted by this support. Now, that is how we can calculate the reaction. Any kind of problems, any type of problems, we can solve like this. Now, in this problem, I have to calculate the reactions. To calculate the reaction RA and RD, now I have taken the moment about A, that is sigma MA is equal to 0. Now, not necessarily to do like this. Now, you can consider that is sigma D is equal to 0, sigma MD is equal to 0. We can take sigma MD is equal to 0 also. When you take this sigma MD is equal to 0, then this creates clockwise moment and these two creates anti-clockwise moment, and you will get the same answer again, isn't it? But whereas in this case, when sigma MD is equal to 0, see, we got RD. Now, when we consider this sigma MD is equal to 0, then we are going to get RA, isn't it? Now, this becomes 0 when you consider the moment at this point. Now, this becomes 0 RD. Then RA will get it. Now, anyway, we can do it. Sigma MA is equal to 0, sigma MD is equal to 0. Anyway, according to your convenience, you can calculate the reaction RA and RD. And again, the another thing our students should know about the uniformly distributed load. How to consider the uniformly distributed load for computation purpose. For computation purpose, how to consider this uniformly distributed load. To calculate purpose, for calculation purpose, now I have done like this. See, now there is one reaction. This is one reaction. This is another reaction. There are reaction. This UDL, uniformly distributed load, is acting over the entire span. Now, this can be converted into a point load. Now, that is intensity of the load for 1 meter distance, W kilonewton, for next 1 meter, W kilonewton, for next 1 meter, W kilonewton. Therefore, the total length is L. Therefore, W plus W plus W, or W into L, total length. That gives you this is the point load. And it is assumed that the point load is always acting at now in the uniformly distributed load, it is assumed that the load is acting at the center of it, that is over the span. Whatever may be the length. Now, when we consider this, this W kilonewton, now here I have converted into point load. The point load is equal to W L kilonewton, isn't that total? Now, here what I did, I have divided this into 2 point loads. Now, that is half of the span. This is half of the span, that is L by 2. And now, in this L by 2, the load acting, now this WL kilonewton is the total load. I have made WL by 2 half. This is half of the load, and this is half of the load. The entire UDL I have converted into 2, that is point loads. Now, it is again half of this load is equal to WL by 2. Where it is acting? It is acting at the center, acting the center of its run. From here to here. Now, similarly, I have done this. That is half of the load, WL by 2. WL by 2 is half of the load, again acting at the center. This is not run center of its run. It is between. And similarly, see, I have converted this UDL into 4 point loads. 1, 2, 3, 4 point loads. Isn't it? Now, this is most important. One should know how to calculate, how to convert the UDL into point loads. And also, we should know when we convert the UDL into point load, where it is acting. The point load is where the point load is acting. Now, therefore, now in this case, see, the same beam, same UDL, I have converted this only 1 point load, it is WL kilonewton. Now, whereas here, I have converted this same beam converted into 2 point loads. One is WL by 2 kilonewton, the other one is WL by kilonewton. Whereas here, in this case, I have done 4 point loads. That is, 1 point load is WL by 4, WL by 4, WL by 4, W. Sum of this is equal to total load. Total load WL kilonewton, WL kilonewton, total load. Isn't it? That is how we should know how to divide the UDL or convert the UDL into point loads. Now, always remember more number of divisions, more number of point loads will give you the better result always. But depending upon the convenience, depending upon the time availability and importance, you must divide this UDL, you have to convert this UDL into point loads. Number of point loads that you should decide it now to convert this UDL into point loads. You can consider only one, you can make it 2, you can make it 4 point loads, or any number of point loads can be, you can do it. Isn't it? So please remember this, don't forget this. And the shear force, already we have discussed about this number of times, because there are many other new entrants they are participating in the lecture class. Now therefore again, the shear force, algebraic sum of all the vertical forces, either the left side or right side of the section. Algebraic sum of the forces. Now if you want to calculate the shear force at this point, consider all the vertical forces in this right side or to the left. And also, you please remember the sign convention. Now when I am calculating the shear force at this section, if you consider the left hand side, then the result, sum of the forces, upward force, downward force, sum of these two, if you get the result upward, it is positive, and vice versa. And similarly, if you calculate the shear force at any section, and from here to here, wherever you calculate it, now let us consider, only we should consider either left hand side total number of forces or right hand side. Isn't it? Sum of that is forces either to the left side or to the right side of a section in a loaded beam. Isn't it? Now if you get the result left side, if you consider the section here, if you get the result left hand side, then if you get the negative downward result, then it is negative shear force. Isn't it? Now and vice versa. Now this is how sign convention is adapted in our discussions throughout the subject. And bending moment, again, it is again algebraic sum of all the moments in a loaded beam at any section is algebraic sum of the moments either to the left side section or to the right section. Isn't it? Now if we calculate the bending moment at this point, now consider all the forces, moment of all the forces in the right hand side. Isn't it? Now similarly, or you consider all the forces which are acting, the moments of all the forces in the left hand side. We will discuss about that. Now we will solve few problems. And again, now here, sign convention. Now see, normally the deflection is usually in this form. Now this kind of, suppose due to in a loaded beam, if it deflects downward, the moment occurs in this type of beam are sagging bending moment. This sagging bending moment, I have considered it is positive. And suppose if the beam deflects in this shape, now then it is sagging bending moment, and this is hogging bending moment. Now this is positive bending moment, and this is negative bending moment. And similarly, now this is hogging. Very rarely this type come across in our design, in our lifetime structures. Now normally, these are the method we are going to adopt it in our future discussion. Now this is positive bending moment, sagging bending moment, downward deflection, and this is downward deflection, upward deflection, that is positive bending moment, sagging, and this is hogging bending moment. And similarly, this is again hogging bending moment. This is what we have adapted in our discussion throughout. Isn't it? I think we have discussed a number of problems, how to solve the problem, draw the bending moment and shear force diagram. Now first, read the problem very carefully. Now read and write this. Now in this case, the diagram is given. Now sometimes the diagram may not be given. They will explain and ask you to draw the bending moment and shear force diagram for the given beam. Now whereas in this case, now it is given. In this case, see, now this is the beam given. They are given the beam. Now this beam they are given, and for this beam we need to draw the bending moment and shear force diagram for this beam. Now there are 3 steps to be followed. Number 1, first step, That means first we have to find out the reaction. RA is equal to how much? Now this is the result I have written. Not, it will not be given in the problem. And the only beam and load distances are given, span will be given in the question. Now this is we have calculated. That is step 1. Sigma V is equal to 0. Conditions of equilibrium. That is first condition of equilibrium. Sigma V is equal to 0. Now here sum of all the three forces, all the forces, all these forces are acting downward. And this is cantilever beam. Now in this cantilever beam, there is only one reaction, fixed end, fixed support. Now when the force 1, force 2, force 3, force 4 and force 5. There are 5 forces are acting downward. Therefore, we have only one support to this condition, this type of beam. Now therefore, this beam has only one support and the entire, all the 5 loads are resisted by this, isn't it? Sum of the 5 forces downward is equal to sum of the, that is only one reaction, it is acting upward. That is what I have written there straight away. Now, see, now this is 4 into 2, 8 kilonewton, plus 2 kilonewton, plus 2 kilonewton, plus 2 into 2, 4 kilonewton, that is, and 2 kilonewton. There are 1, 2, 3 point loads and 2 UDLs are acting down. The total sum of the forces, that is RA is equal to, sigma V is equal to 0. For this condition, that is RA is equal to all the downward forces. All the downward. This is the step 1. As soon as we complete this step, we can plot the shear force diagram. Now see, now here, now carefully listen, now follow this. Now when we calculated sigma V is equal to 0, when we got the sigma V is equal to 0, now let us draw the shear force diagram. Now take a reference. Take one reference below the beam. Now you draw. See, this is the reference 0 reference, 0 line. This is 0 line. Now here RA, reaction at A, that is 18 kilonewton, is acting upward. Is acting upward. Therefore, let us go up by 18 kilonewton. Draw a line, vertical line, that is 18 kilonewton. Now at this point, where is 18 kilonewton here? And then from here to here, there is 4 kilonewton per meter is acting downward. 4 into 2, 8 kilonewton. Therefore, 8 kilonewton is acting downward. It is linearly varying because now this is the uniformly distributed load. Now therefore, see over a span of 2 meters, there is 8 kilonewton load is acting down. Therefore, come down by 8 kilonewton. When you reach this 8 kilonewton, then see, now this is the rest remaining is 18 we have gone up, 8 we have come down, and 10 remains here, 10 kilonewton. Isn't it? And similarly, that is 2 kilonewton force is acting downward at this point B. This 2 kilonewton is acting downward. Therefore, you come down by 2 more kilonewton, 2 kilonewton. Draw the line below this, exactly below this. It is 2 kilonewton is acting downward. Now, when you reach this point, the remaining shear force here is 88 kilonewton. From here to here, if you measure this, 8 kilonewton. And similarly, if you calculate the shear force at this section, that is 2 plus 2 multiplied by 2, that is 4 kilonewton. 2 plus 4 plus 2, that means 8 kilonewton is acting downward, isn't it? Therefore, the shear force to the right of the section, shear force to the right side section is 8 kilonewton, isn't it? And similarly, if you consider this side, again, now you will get the same answer. Now therefore, now wherever you calculate the shear force, we will get the same answer. Either you have to consider the right hand section or to the left hand side. Now this is how we should calculate the shear force. Now therefore, from here to here, wherever you calculate the shear force, you will get 8 kilonewton. If you consider this section, right side, that is shear force, 2 kilonewton, 4 kilonewton, and 2 kilonewton. Therefore, 8 kilonewton. All over, that is from B to C, wherever you calculate the shear force, we will get the same answer. That is 8 kilonewton. Isn't it? Therefore, you draw the constant line, horizontal line. This is the shear force line. And again, we are at this point, 2 kilonewton is acting downward straight away. Therefore, go down 2 kilonewton down. That is 2 kilonewton down. And from here to here, the rest is 6 kilonewton. 6. If you measure this, you will get 6 kilonewton. Isn't it? And similarly, from here to here, it is UDL 2 into 2, 4 kilonewton is acting downward. It is linearly varying. Therefore, continuous downward force acting. Therefore, from here to here, let us come down by 4 kilonewton. When you reach this 4 kilonewton, see this is the 4 kilonewton. 4 kilonewton, we have come down here. And again, at point D, again only 2 kilonewton is acting downward. Now this is, and complete this diagram that will give you the bending shear force diagram. That is the shear force diagram. And according to our convention, sign convention, see, if we calculate the left hand side, we will get the upward result. Isn't that? 4 into 2 plus 2, that is 4 into 2, 8 plus 2, 8 kilonewton, and 18 is acting upward. Result is 8 kilonewton. Therefore, if we calculate consider the left hand side, the result is upward force. If we calculate consider the right hand side, the result is downward. Therefore, according to our sign convention, this is positive shear force diagram. Isn't it? This is the positive shear force diagram. Now, this is the step 2. The step 1 is only to find out the reaction. Considering the entire beam section, calculate the reaction. That is the step 1. And step 2 is to plot the shear force diagram. Isn't it? See, after plotting the shear force diagram, we can write down FD, that is shear force at D is equal to 2 kilonewton. Shear force at C is equal to 8 kilonewton. Shear force at B is equal to 10 kilonewton. And shear force at A is equal to 18 kilonewton. Now this completes the 2 stage, isn't it? Two steps. And here at this point, there are 2 shear force, that is 10 kilonewton and 8 kilonewton. There are 2 forces, isn't it? Shear force at point B is 10 kilonewton and 8 kilonewton. Therefore, now the section will be designed for 10 kilonewton force, isn't it? Shear force. Now that completes drawing the shear force diagram. And similarly, now that is to calculate the bending, to draw the bending moment diagram. That is the third step. Step 3. Step 3. Now to calculate the bending moment. Now we know that that is the free end. Bending moment at the free end is equal to 0. MT is equal to 0. And the bending moment. Now see, normally we can calculate the bending moment all over. That is from one free at all the points. We can calculate the bending moment. Now, normally what we do, we'll calculate the shear bending moment only, or shear force only at the critical points. Critical points where the loads are acting. Now, or else, wherever we want, we can calculate the bending moment or shear force. Now, normally to plot this diagram, we'll calculate few silent points, that is critical points where the load is acting. So therefore, bending moment at D is equal to 0. Bending moment at C is equal to, according to definition, consider either to the right hand side or to the left hand side. Now, according to your convenience, you can consider either right hand side or to the left hand side. Now, see, bending moment at C is equal to, here 2 kilonewton is acting. That is 2. Distance is 2 meter. Isn't it? Distance is 2 meter. The bending moment at point C is equal to 2 into 2. That is what we have written here. 2 into 2 kilonewton. 2 kilonewton into 2 meter. And if you consider the second load, that is UDL. Now this UDL is equal to 2 multiplied by 2. Where it is acting? It is UDL. Already I have explained. This is the UDL. The way it is assumed 2 into 2, that is 4 kilonewton is acting at the center. It is assumed that it is acting at the center. That is for calculation purpose, this UDL is converted into points. This is not. That UDL we have converted into point load. And this point load is acting at a distance at the center of the UDL. Now therefore, 2 into 2, 4 kilonewton, 2 into 2, distance from here to here, it is perpendicular distance, that is 1 meter. Therefore, the bending moment at this point C is equal to 8 kilonewton meter. 8 kilonewton meter. And if you consider the point B, if you calculate the bending moment at this point, if that is MB, moment, bending moment at B is equal to. Now see, this is 2 kilonewton force. Where it is acting? It is acting at a distance 4 meter. That is 2 into 4, I will tell you. And similarly again, the second force, that is UDL. UDL already we have calculated, it is 2 into 2, 4 kilonewton, which is acting at the center. Now therefore, from here, it is 2 plus 1, it is 3 meter. It is 3 meter. 2 into 2, that is load into distance. That is from here to it is 3 meter. That is what I have written. And similarly, there is another force, that is 2 kilonewton, is acting downward at a distance 2 meter from point B. Now there is 2 into 2, 2 multiplied by 2. No, 2 multiplied by 2. Now therefore, it gives 24 kilonewton meter. 24 kilonewton meter. And similarly, at this point, bending moment at A, that is right hand side. Now therefore, see, this is 2 kilonewton multiplied by 6 meter. 2 kilonewton multiplied by 6 meter. And all are creating clockwise moment with respect to point B, point A. Now therefore, that is 2 multiplied by 6 meter. 2 multiplied by 6 meter. Plus the second force, that is 2 into 2. 2 into 2. At a distance 5 meter. That is 2 plus 2 plus 1. It is assumed that it is acting at the center. That is therefore 2 multiplied by 2 multiplied by 2 at a distance 5 meter. That is 2 plus 2 plus 1. That is 5 meter. And similarly, the another force, that is 2 kilonewton. That is 2 plus 2, 4 meter. With respect to A, from here to here it is 4 meter. Therefore, 2 kilonewton into 4 meter. From here to here, 4 meter. And similarly, another force, that is 2 kilonewton. It is again creating clockwise moment with respect to A. Therefore, 2 into 2, it is 4 kilonewton. 2 into 2, it is 4 kilonewton. 2 into, it is 2 into 2, 2 into 2. That is 2 kilonewton force into distance, perpendicular distance. Plus again, it is 4 into 2 meter. That is 4 into 2 meter. Intensity of the load, that is UDL. Another UDL. And where it is acting, it is assumed that it is acting at the center. Therefore, distance to the center is 1 meter. That is what we have written here. Now, therefore, now we get, see, that is 22 kilonewton meters. Kilonewton meter is the bending moment at this point. Isn't it? And then to plot the bending moment diagram, always take a reference, that is 0. See, according to our sign convention, now this is arcing bending moment. It is arcing bending moment, it is negative bending moment. We have taken this, we have considered this as negative bending moment. Now therefore, now when it is negative bending moment, we need to draw the bending moment diagram below the reference line. Now see, if you have calculated the bending moment here, at MC 8 kilonewton meter. Now therefore at MC, that is below this 8 kilonewton meter. You mark a point here, that is measure this distance 8 kilonewton meter. And similarly, that is at B we have 24 kilonewton meter. Now you measure this 24 kilonewton and mark a point, isn't it? And similarly, that is at MA we have, that is 52 kilonewton meter. Again you mark this, isn't it? See, now here, now at this point, now the bending moment at D is equal to 0, bending moment at C is equal to 8 kilonewton meter, bending moment at B is equal to 24 kilonewton meter, and bending moment at A is equal to 52 kilonewton meter. Isn't that? Now you join all these points will get the and complete the diagram that gives you the bending moment diagram. Isn't that? Now here let us remember, this is UDL, uniformly distributed load. The bending moment diagram always below UDL is a curve or a parabolic line. This is a parabolic line. And between this, here in between this, the bending moment is linear variation. It is linear, isn't it? And similarly, again below this UDL, again it is a curve. Now this is the shape of the bending moment diagram. Now the advantage of this bending moment diagram is what is the necessity of plotting this bending moment diagram? To plot, the necessity of plotting the bending moment is to measure or to calculate, instead of calculating the bending moment at every point. Normally what we will do, we will calculate the bending moment at the critical points. Moment are forces, shear forces at the critical points. Then we will plot this. From there, directly we can measure the shear force. From here to here we can measure the shear force. From here to here we can measure the bending moment. From here to here we can measure the bending moment. And from wherever you want, directly we can measure the bending moment. And normally these are plotted. These are the bending moment and shear force diagrams are plotted for some scale. Now according to your convenience, this is not scale. Now let us go ahead with the next problem. Now one more problem of the similar kind. Now till now we have discussed about the cantilever beams. How to plot the bending moment and shear force diagram for cantilever beams. Now we will take up that to draw the bending moment and shear force diagram for the simply supported beam. How to draw the bending moment and shear force diagram for isn't it? Now therefore, in this problem what they have given, let us see. Draw SFT and BMD for simply supported beam of span L subjected to a point load W kilonewton at its center. Now therefore, when the load is acting, first draw the bending beam diagram. First draw the beam diagram, and when you draw this beam diagram, W kilonewton is acting downward, and at the center. Now when you look at the beam is symmetrically loaded. The beam is symmetrically loaded. Isn't it? The beam is symmetrically loaded. When the beam is symmetrically loaded, the reaction, that is one reaction support, the other support. There are two supports, isn't it? But both the supports are carrying equally. This load is equally carried by both the supports. Therefore, RA, reaction at A, and reaction at C is equal to W. RA plus RB, sum of these two reactions is equal to total load on the beam, W kilonewton. Isn't it? To calculate this, now sigma MA is equal to 0. Sigma MA. Step 1. Please understand, this is the step 1 to calculate, only to calculate the reactions. Now therefore, RA plus RC is equal to W kilonewton here. W kilonewton. RA plus RC. This is RA, and RC is equal to total load W kilonewton. Isn't it? Sigma MA is equal to 0. When you consider sigma MA is equal to 0, now with respect to this A, that is, this reaction creates anti-clockwise moment and this load creates clockwise moment. Therefore, for equilibrium condition, sum of the anti-clockwise moment is equal to sum of the clockwise moments. Now therefore, when sigma MA is equal to 0, taking moment about A, that is RC multiplied by L. This is RC multiplied by L. RC is the reaction and L is the length, perpendicular distance, is equal to W, load, into distance, L by 2. That is L by 2. Therefore, now we know that RC plus RC is equal to W kilonewton. RA plus RC is equal to W kilonewton. RA plus RC is equal to W kilonewton. Now therefore, RC is equal to RC is equal to W into L by 2. Half of the load, that is half of the load is taken by this support and half of the load is taken by this support. Isn't it? Now this is how we can calculate the reactions. Isn't it? Now whereas the step 2, second step, how to draw the shear force diagram. To draw the shear force diagram, immediately after calculating the reactions, what we should do, how to do this, Now, after, see, W kilonewton, half is resisted by this W by 2, half is resisted by this. Reaction A, W by 2 kilonewton. Reaction C, W by 2 kilonewton. Isn't that? Now, therefore, now what we should do now to draw the diagram, shear for diagram. Now, take a reference, 0 reference. This is 0. From 0, now see, RA, W by 2 kilonewton is acting upward. W by 2, half of W by 2, upward. Therefore, let us go up by W by 2 kilonewton. Isn't it? And if you calculate the shear force at any point, consider the left hand side, W by 2 kilonewton is acting upward. If you consider the right hand side, W is down, W by 2 is up. Therefore, net sum of these two is equal to W by 2 downward. If you consider the left hand side, W by 2 is upward. If you consider the right section, W by 2 is downward. Now, therefore, that is at all the points from here to here, that is from A to B, that is shear force is W by 2 kilonewton all over the B from A to B. Now, we have gone up to W by 2 kilonewton and draw this line, and at this point W kilonewton is acting downward. Therefore, already we are above the W by 2. Now, from here draw a line, that is shear force line W. W by 2 is half above and W by 2 is below. Therefore, W by 2 is not. This total is W kilonewton. Above W by 2 and below W by 2 kilonewton. Now, if you consider the shear force at this point, if you consider the right hand section, now this is upward, isn't it? Right, upward. Right section, upward. If you consider the left section, W downward and RA upward. W minus W by 2, W is acting downward. If you consider the left hand section, W by 2 downward. If you consider the right section, W by 2 upward. Now, therefore, is it not? Now, at all the points from here to here, W by 2 shear force is acting upward. Therefore, let us draw this continuously up to this point. Then, at this point, W by 2 is acting upward. Let us go up now and reach the 0 point, reference point. Therefore, now this complete this diagram. Now, this gives us the shear force diagram for the given loading, for the given beam. Now, here, now if you consider this, left up shear is positive, left side section upward positive, and right side it is again we will get the vice versa downward at this section. Now, this is positive. If you consider this section, now your left side, that is net is downward, W minus W by 2, W by 2 is down. Now, therefore, W by 2 is down, left side. If you consider the right side, W is acting upward. Now, therefore, according to sign convention, this is negative. This is positive shear force and this is negative shear force. Now, therefore, the maximum shear force in the beam is equal to plus, that is maximum positive shear force W by 2 kilonewton and maximum negative shear force is W by 2 kilonewton. Isn't it? Now, this is how we can plot the shear force diagram. And similarly, that is to plot the bending moment diagram. To plot the bending moment diagram, that is step 3, that is the third stage, that is in solving this problem. Now, see, for the given beam, bending moment at A and B, bending moment at A and B, they are simply supported ends. The bending moment will be 0. MC is equal to 0 and MA is equal to 0. And in the bending moment occurs all over the beam except at A and C. MC is equal to 0 and MA is equal to 0. Now let us calculate the bending moment at the center of the span at this point. Isn't it? To calculate the bending moment at the center of the span. Now, to calculate the bending moment at the center of the span. Now, see, very simple analysis it is. Now let us see the section where we need to calculate the bending moment. Therefore, consider the right hand section. If you consider the right hand section, W by 2 kilonewton is acting upward and distance L by 2. W into W by 2 into L by 2 of distance. Now W into L by 2. Or if you consider the left section, that is W into W by 2 into L by 2. Therefore, the bending moment at this point is WL by 4 kilonewton meter. And to plot this again, draw a reference line, zero reference line, and at the center of the span at B, there is WL by 4 kilonewton is acting. Therefore, draw this, locate this point, and join this point. That will give you the, you will complete this diagram. That gives you the bending moment diagram. Now this is the bending moment diagram. Shows the variation of bending moment across the beam. Bending moment is across the beam. Now at this point it is maximum bending moment because it is a critical point where the load is acting. Now therefore maximum bending moment occurs at this point. What is the bending? The bending occurs, the maximum bending is that is at this point. It is a critical point. Now therefore W by 2 into distance or W by 2 into distance. That it gives us the same thing. And according to our sign convention, this type of beam deflects in this shape, in this form. Therefore, when the beam deflects in this form, now it is W. That is when this deflects in this form. That is sagging bending moment. The sagging bending moment we have considered the positive bending moment. Now, therefore, it is positive bending moment. Now, from this diagram, we can measure the bending moment at all the points, and accordingly we can design the section. We are designing this to the maximum bending moment. See, any beam, whatever the beam you are designing, or maybe steel beam, wooden beam, or concrete RCC, whatever you design it, now we are designing the beam. We are designing the beam for the maximum bending moment, and we will adapt through the section. Isn't it? Now that is the advantage of calculating the bending moment. And similarly, let us solve one more problem of the similar kind. See, again, first to read the problem carefully. Carefully read the problem. Then plot this diagram. That is load diagram. Now when you plot this diagram, first calculate the reaction RA and RB, RC. Let us calculate the reaction. Now for the given problem, this is the diagram. This is the beam diagram. Isn't it? See, after writing this diagram, after drawing this diagram, reaction A and reaction C. There are two reactions. Only one load is acting. Isn't it? Now from here to here it is 1 meter and the rest is 3 meter. Isn't it? Therefore, one force is acting downward and there are two reactions upward. Therefore, RA plus RC is equal to 4 kilonewton. RA plus RC is equal to 4 kilonewton. RA plus RC is equal to 4 kilonewton. Isn't it? Now, therefore, to calculate the reaction, sigma ME is equal to 0. Sigma ME. Second, that is conditions of equilibrium. Sigma ME is equal to 0. When you consider this sigma ME is equal to 0, that is RC into distance 4 meter. RC into 4 meter. RC into 4 meter and then 4 into 1 meter. Isn't it? That is anti-clockwise and this is clockwise. Now then RC into 4 meter and 4 into 1 meter. That is one is negative, the other one is positive. Therefore, reaction 4. Now we will get RC is equal to considering the sigma ME is equal to 0 and calculate the reaction RC. RC, if you calculate the reaction RC, that is you will get 1 kilonewton. Isn't it? Therefore, when you get the RC is equal to 1 kilonewton, then RA plus RC is equal to 4 kilonewton, then RA plus 1 is equal to, now therefore RA will get 3 kilonewton. Now, when you look at the diagram, now you can straight away we can write down what is RA, how much RA, how much RC. Now, because there is 4 kilonewton is acting, isn't it? It is at the 1/4 distance, and this is at the 3/4 distance. Therefore, less force is received by this support, and more force is received by this support. Now, therefore, RA is equal to, that is 3/4 load taken by this, because it is near to the reaction RA. Now, when you look at this, we can say no, don't worry about that. You just calculate like this. Then you will get RA is equal to 3 kilonewton and RC is equal to 1 kilonewton. And when you get the value for RA and RC, now let us plot the shear force diagram. To plot the shear force diagram, see, take the reference, and then 3 kilonewton is acting upward. Then let us go by 3 kilonewton. Now, if you calculate the shear force at any section between these 2 points, now right side, 4 is acting down, and 1 is acting up. Now, therefore, net is 3 kilonewton is acting downward. If we calculate the reaction shear force at any point between, now we will get that is 1 is upward and 3 downward. That is sum of these two is equal to 3 kilonewton downward. Now, therefore, between this and this point, therefore, at all the points from here to here, that is 3 kilonewton force is acting, that is shear force available occurs. Isn't it? Now, when you reach this point, now continue this line, shear force line, then continue this. Now, here 4 kilonewton is acting downward. 4 kilonewton come down by 4 kilonewton. Already we have 3 kilonewton upward above the reference. Now, just come down by 4 kilonewton. When you already we are in 3 kilonewton above the reference, and next go down by 1 kilonewton. That is from here to here it is 4 kilonewton. From here to here it is 4 kilonewton. Therefore, 3 plus 1, 4. Above it is 3 kilonewton. Below it is 1 kilonewton. And if you calculate the shear force from this end, from B to C, anyway, see, we will consider the section. We will take this is the section. Right side, 1 kilonewton is acting upward. If you consider the left side, that is 4 kilonewton minus 3 kilonewton, 1 kilonewton is downward. Isn't it? 1 kilo. If you consider the right section, 1 kilonewton upward. If you consider the left section, it is 1 kilonewton downward. Now, therefore, all along this beam, or from B to C, wherever you calculate, we will get the 1 kilonewton. Therefore, continue this shear force line, and then at this point, 1 kilonewton is acting upward. You will go up by 1 kilonewton. You will reach the zero. Now, this complete the diagram. Now, this gives you the shear force diagram. Now, according to our sign convention, left side up result is upward, then positive. Now, if you consider the right side is upward, it is negative. Now, therefore, negative shear force diagram. And similarly, now to plot the bending moment diagram, we know that the bending moment at A and bending moment at C is 0 because it is simply supported in, isn't it? And the maximum bending moment occurs below the load, that is critical point. Maximum deflection occurs at this point. Now, therefore, at this point, let us calculate the bending moment at this point. That is 1 multiplied by 3 meter. 1 multiplied by 3 meter. 1 multiplied by 3 meter. That is the bending moment at this point. Now, if you consider the right hand side, if you consider the left hand side, it is 3 kilonewton multiplied by 1 meter. Now, therefore, again it is 3 kilonewton meter. Now, this is what MB bend moment at B is equal to 3 kilonewton meter. And similarly, now again let us draw the bending moment shear force diagram, bending moment diagram. To draw the bending moment diagram, take a reference. This is the reference, and this is the critical point. Now, at this point, we have calculated the bending moment. Now, therefore, measure this distance and mark this point. We will get 3 kilonewton meter. And now, join these points. Now, this shows the variation of bending moment across the beam or across the beam. Now, complete this diagram. You complete this diagram. This gives you the bending moment diagram. Now, this bending moment here plus is missing. Now, please note this is the plus, that is positive bending moment. Now, because it is a sacking bending moment. Now, due to this load, for this condition, the deflection occurs, rotates only in this direction, like this only. It has to deflect in this direction only and rotate in this direction only. Therefore, it is a positive bending moment diagram. This is how this completes the problem. So this carries 10 marks normally in the examination. And also let us we must write. Also we must write. The probability is asked. Mention the maximum bending moment and maximum shear force. Maximum bending moment and maximum bending moment. It is maximum positive bending moment. Is equal to 3 kilonewton meter. 3 kilonewton meter. Sorry, some 3 is missing here somewhere. Meter is missing. It is 3 kilonewton meter. 3 kilonewton meter is the maximum bending moment, and that is maximum positive shear force is 3 kilonewton. Maximum negative bending moment is 1 kilonewton. Maximum positive bending moment, positive shear force. Maximum positive shear force is 3 kilonewton, and maximum negative shear force is 1 kilonewton. That completes the problem. That completes the problem. Then we will go for, let us solve one more problem. See another problem. Now already we have discussed in the similar way. There are two reactions. Read the problem carefully. Then plot this diagram. This is how you have to proceed. Now there are 3 point loads. One is 2 kilonewton, 4 kilonewton, and 2 kilonewton. It is 4 meter distance. 1 meter, 1 meter, 1 meter, 1 meter. That is, it is given in the problem. It is, see, it is 1 meter, 2 meter, and 3 meter from the left hand support. But it is missing here 1 meter, 1 meter, 1 meter, 1 meter. That is, the first is 2 kilonewton, 4 kilonewton, and 2 kilonewton. Two reactions, RE and RE. Sigma V is equal to 0. Therefore, RA plus RE is equal to 2 plus 4 plus 8. 8 kilonewton is acting total load, isn't it? Sum of the upward reaction is equal to sum of the downward forces. This is what we have written. See, after considering or calculating the bending, considering the moment, that is sigma MA is equal to 0. Now, this is RE into 4 meters is equal to, that is 2 into 3 meter plus 4 into, that is 2 meter plus 2 into 1 meter. Now after doing this, we'll get that is RE is equal to 4 kilonewton and RE is equal to 4 kilonewton. Otherwise, straight away we can write down. Simply we can when you look at this beam, the beam is symmetrically loaded. That is, from here it is 1 meter, from here it is 1 meter, and from here to here it is 1 meter, from here to here it is 1 meter. The beam is symmetrically loaded, doesn't it? So therefore, now it is very easy to calculate. Now immediately after calculating the reactions, then compute this diagram now. Isn't it? Compute this diagram. It is, see, we can check it here. We can go through this. Now see, RE is equal to 2 plus 2 plus 2, 2 plus 4 plus 2, 8 kilonewton. Half is taken by this and half is taken by this support. There are two forces are acting. Isn't it? Now, see, immediately after calculating this, we can draw the shear force diagram. To draw the shear force diagram, again, take reference, 0 reference. Now here RA is acting upward. Go by 4 kilonewton. Go upward, draw the line, 4 kilonewton. Then, if we calculate the shear force at this point, at this section, anywhere between A and B, now anyway, from here to here, anywhere if we calculate the shear force, now we will get only 4 kilonewton. If we consider the left hand side, we will get 4 kilonewton is acting upward. If we consider the right hand side, 8 kilonewton is downward and 4 kilonewton is upward. Result of this, sum of this is equal to 4 kilonewton. Anywhere between this and this. So this is continue this constant. Shear force is constant between A and B. Now this is, draw this line. And at this point, 2 kilonewton is acting downward. 2 kilonewton is acting downward. Therefore, you come down 2 kilonewton here. Isn't it? Now come down by 2 kilonewton. Now from here to here, it is left with 2 kilonewton. 2 kilonewton shear force. And then, if we calculate the shear force at this point between C and B and C, anywhere between B and C, so you just calculate that is 4 is acting upward and 2 is acting downward. 4 is acting upward, 2 is acting downward. if you consider the left hand side, the result is 2 kN is acting upward. 2 kN is acting upward between from here to here. Or if you consider the right hand section, 4 plus 2, 6 kN is acting downward and 4 kN is acting upward. Therefore, that is sum of these, all these three forces gives you that is 2 kN down. That is 4 plus 2 minus 4. That is equal to 2 kN is acting down. Therefore, from here to here you will get 2 kN. Isn't it? Continue. Now draw this line up to this point, and at this point 4 kN is acting downward. 4 kN down acting downward. Already we are 2 kN above the reference. Then 2 more kN come down. Then draw this line continuously 4 kN. From here to here it is 4 kN. And after this, at this point, if you calculate the shear force, 4 kN is upward, 2 kN is downward. Therefore, 2 kN is the net force. Or if you consider the left section, left hand side, 4 plus 2, 6 kN is downward and 4 kN is upward. Now, therefore, what is going to happen? How much you are going to get it? 2 kN. From here to here, you will get the 2 kN force. Now, draw this line, continuously up to this, below this line. And then at this point, at D, 2 kN is acting downward. Therefore, that is 2 kN already we have down from the reference to here and 2 more kilometers. Therefore, we will get 4 kN. And if you calculate the shear force between D and E, along this, between D and E, we will get that is 4 kN shear force. 4 kN upward. If you calculate the right side, 4 kN downward. Now, therefore, now at this point, 4 kN is acting upward. We go up by 4 kN and reach 0 reference line. Now, this completes the diagram. That is the shear force diagram. Shear force diagram. Isn't it? Now, this shows the variation of shear force across the beam. According to our same convention, left upward. If you consider this left side upward, or right side downward force is equal to, it is positive. And here, if you consider this side, now it is negative shear force. Now this completes the shear force diagram, isn't it? Shear force. And in the third stage, now let us calculate the bending moment. To calculate the bending moment, how to calculate the bending moment? Now already we know that is A, that is at A and E, bending moment is equal to 0. At A, because it is simply supported end. Simply supported end, bending moment is equal to 0 at A, bending moment at E is equal to 0. Now to calculate the bending moment at D, now here it is at D. Now see, very simple. Consider the right section. 4 multiplied by 1, it is 4 kN. 4 multiplied by 1. If you consider C, 4 multiplied by 2 meter distance, 4 into 2 meter distance, that is anti-clockwise. And this is 2 into 1, that is 2 into 1. It is clockwise. One is anti-clockwise, the other one is clockwise. Therefore, we will get 6 kN/meter 4. Isn't it? And similarly, at B also, consider the left section 4 into 1 kN. 4 into 1 kN. Now that completes the calculation part, computation part. Then take a reference, 0. Then below this, 4 kN is acting. Now measure this distance to some scale and plot this point. And similarly, at C, measure this point. It is at here, that is 6 kN/meter. And again at below D, it is 4 kN/meter. Now join all these points. And this gives, now this is the bending moment diagram. For the given loading. And also in the problem it is asked, they have mentioned they have asked to mention the maximum bending moment and shear force. Now from this diagram, there are two maximum shear force. One is positive shear force, that is 4 kN. The other one is negative shear force, 4 kN. And here the maximum bending moment, it is, that is 6 kN/meter at the center. And you please remember here, the one important thing we should remember here, always the bending moment is maximum. where the shear force changes its sign. Now the shear force, now here, now this is positive shear force and this is negative shear force. Now at this point, the shear force changes its sign, positive to negative or negative to positive. Now at that point, the bending moment is always maximum. This is the maximum bending moment. Now that completes the bending moment diagram. That completes the bending moment, plotting the bending moment diagram. Okay. Now let us discuss one more problem. A simply supported beam of span 1 meter is subjected to a UDL of W kilonewton per meter run throughout its length. Draw SMD and BMD and calculate the maximum bending moment. Now, as usual, it is W kilonewton meter. Load is acting over the span, entire span. That is, therefore, total load is equal to W multiplied by L. WL kilometer. In 1 meter distance, W kilonewton. Another 1 meter distance, W kilonewton. Another 1 meter distance, W kilonewton. Like that is depending upon the distance. Total distance multiplied by W kilonewton. Therefore, total load acting on the beam is W kilonewton. WL kilonewton meter. Sorry, WL kilonewton. Now, there is one UDL is acting downward, and there are two reactions, RE and RB. There are two reactions acting above. Acting above, the RA and RB is reaction acting above, and the load acting downward. Therefore, RA plus RB is equal to total load. Total load is equal to W into L. W into L. Total load is equal to W into L. Total load is equal to W into L. To calculate the bending moment, to calculate the reaction, the secondary conditions of equilibrium, sigma V is equal to 0, RA plus RB is equal to W into L kilometer total load. And to calculate the reaction, right? RA is how much and RB is how much. That is taking moment about A. Now taking moment about A. Now here taking moment about A. So sigma ME is equal to 0. Therefore, RB reaction RB into distance. RB into distance. RB into distance. RB is equal to, that is RA and RB. RA and RB is equal to Now this is W, RA and RB. Now this is sigma ME is equal to 0. When sigma ME is equal to 0, that is RB multiplied by distance. RB into L. RB into L. Mine is equal to, that is WL into L by 2. Because WL is the total load. WL is the total load which is acting at the center. Therefore, when you consider the moment about this point, this RA, RB into distance, RB into L, RB into L, RB into L, RB into L minus WL at a distance L by 2. Isn't it? At a distance L by 2. Now, therefore, now we will get RA is equal to, after solving this, we will get RA is equal to WL by 2. RB is equal to WL by 2 and RA is also WL by 2. Total load is WL. Now, when you look at the beam, straight away we can write down that is what is the total load shared by RA and load shared by RB. Straight away we can write it down. We can write it. We can see, when you see this, look at the beam, we can say that is total load uniformly distributing over the span. Therefore, half will be taken by this support and half will be taken by this support. Isn't it? Therefore, total load is WL. Therefore, RA is equal to WL by 2, RB is equal to WL by 2. Isn't it? Another half of the load is taken by this support and half of the load is taken by another support. Isn't it? See, after calculating the reaction, now let us plot the shear force diagram. How to plot the shear force diagram? To plot the shear force diagram, see, now again, see, RE is equal to WL by 2 kilonewton. RE is equal to WL by 2 kilonewton. And RB is equal to WL by kilonewton. Now, after doing this, see, now at this point, at A, WL by 2 load is acting upward. Let us go up with respect to the reference. Consider the reference 0 reference. With respect to this reference, that is WL by 2 is acting upward. WL by 2 is acting upward. Now from here, WL by 2 is acting upward. From this, now from here to here, the WL is acting downward. From here to here, the WL is acting downward. At this point, WL by 2 is acting upward. Therefore, let us go up by WL by 2. Now from here to here, it is WL by 2 is acting, WL is acting downward. We gone up by WL by 2, then let us come down and reach WL by 2. Isn't it? Now therefore total linear variation is WL, W and L, total load. Total load is WL. For example, it is 2 into 4, 8 kN is acting. That is when it is total load is 8 kN, 4 kN is resisted by RA and 4 kN is resisted by RB. Now we have gone up by 4 kN and come down by 8 kN. So see, from here to here it is 4 kN and from here to here it is 4 kN. That is WL by 2 from here to here WL by 2 linear variation. From here to here it is WL by 2 linear variation. At this point, at point B, now this is upward. This is upward 4. You just go up and reach the 0 point. Now this complete this diagram and this gives you the shear force diagram. This is the shear force. This is the shear force diagram. Now this is, if you consider the left hand side, result is upward. If you consider the right hand side, result is downward. Now therefore, it is positive shear force. If you consider the this section, right side is upward, left side is negative. Therefore, it is negative according to our technology. And similarly, to calculate the bending moment, and to draw the bending moment diagram. Now see, now we know that simple support A and B, MA and MA is equal to MB is equal to 0. Bending moment at A is equal to 0. Bending moment at B is equal to 0. Isn't it? Now let us calculate. Now from this diagram, it is seen that at the center, the maximum bending moment. The maximum bending moment is at the center. Now at the center means let us check it. To check this. Now see. Now from the diagram, we can see that shear force is 0 at this point. Where it is 0? At a distance x from the support. Now let us consider this is the x. The bending shear force is 0 at this point. Now let us calculate the shear force from the diagram B, from the force diagram. Now when you calculate the force diagram from this beam, x is equal to L by 2, we will get x is equal to L by 2. When you calculate the shear force at this point, at a distance x, section xx, at a distance x from the right hand support, we will get x is equal to L by 2. That means half at the center, exactly at the center, we will get the maximum, that is the zero shear force at this point, isn't it? This is the center of the span. Now to calculate the bending moment, that is, we know that bending moment at A is equal to 0, bending moment at B is equal to 0. Now therefore, now let us calculate the bending moment at XX, that is MXX. Bending moment at XX, isn't it? Is equal to, how to calculate this? See, to calculate this, WL by 2 into perpendicular distance. Perpendicular distance is L by 2. Load is WL by 2. And this is W, the L by 2 distance. WL by 2 into distance, L by 2 distance. L by 2 distance minus, now one W is missing here. Now this is WL by 2 is the load. To calculate the bending moment, at XX, that is, this force is creating clockwise, anti-clockwise, and this UDL creating clockwise moment. Therefore, now it is bending moment at XX is equal to WL by 2 into L by 2 distance. WL by 2 into L by 2. WL by 2 is the load and distance, perpendicular distance is L by 2. Then minus, that is another force here. The another force is this UDL, W into L by 2. Total load from here to here it is half WL by 2. Where it is acting? It is acting that it is assumed that it is acting at the center. That is L by 4. Now from here it is L by 4. Total load. Now we are converting this UDL into point load. That point load is WL by 2 half of this. Where it is acting, it is an L by 4. Now the term is missing here, minus, isn't it? Now therefore, now when you calculate this, now after simplification, you will get WL square by 8. WL square by 8 kilonewton meter. Isn't it? That is the bending moment at the center of the span for in the uniformly distributed load. Now you please remember this. Now this is forever you need to whenever the design comes. Now normally all the beams and all the structures uniformly distributed load. Then we need to remember this WL square by 8 kilonewton meter forever. Isn't it? Now after doing this, now after calculating this, now you just measure, take a reference, 0 reference, and here at the center, measure this WL square by 8. WL square by 8. This is WL square by 8. Measure this distance and complete the diagram. And it is the parabolic line because it is UDL. Isn't it? No, it is UDL. UDL means it is a parabolic line, curved line. Now you draw this and complete the diagram. And for this loading, it is the bending will be in this shape. Therefore, it is sagging bending moment. Now this sagging bending moment is positive bending moment. Therefore, it is positive bending moment. Now this completes the solving the problem. This kind of problem. Now another problem. Now we'll discuss in the next class. That is on Monday. We will discuss about this. Let us complete this problem, isn't it? Then Monday we'll go through this and we will solve this problem. Thank you very much for all the participants. Thank you so much. Thank you very much for everybody.